What is the common ion? Okay, if you remember Le Chatelier's principle, um, if I add something, I push the equilibria in the direction to consume what I add. So let's look at lead bromide, okay? PbBr2. We know that this breaks up into Pb plus 2 plus 2Br minus. And I can go over to the table and I can see that K is 6.6 times 10 to the minus 6. Now that looks like a small number, but because the expression has an x cubed, this is not really what I would call a totally insoluble salt, okay? Yes, we are going to call it insoluble, but it's definitely not going to be some tiny number. So I could now very quickly calculate for the pure lead bromide. I take some of the lead bromide, drop enough of it so that it doesn't all dissolve, and I ask, what is the concentration of the saturated solution? So I'm not going to draw the ice diagram. I'm not going to say 0 lead and 0 bromide, and then I make X of lead and I make 2X of bromide. I'm just going to simply write the equilibrium expression right from the get-go. So this is equal to X, which is for the lead, times 2X squared, which is the bromide, okay? And this is equal to 4X cubed, okay? That's a 4 there, because the 2 squared. So X is equal to the cube root of K over 4. And if I substitute in 6.6 times 10 to the minus 6, I get 0.0118 molar. Now, I think in Gen Chem 1 you were calling this a insoluble salt, and it isn't that soluble. You can't make a molar solution of it, okay? But you could make a 0.01 molar solution of it, okay? But a saturated solution is 0.0118. Let's say lead is unhealthy for you. And let's say that you got to drink some water, and the water has lead bromide in it, okay? I'm not suggesting you do that, by the way. Well, you're going to get quite a, after you drink 100 liters of water, you've got 1.18 moles of lead inside of you. Okay, that's not so good. So how can I remove the lead from the water? And we can do this with the common ion effect. So if I added another salt, so let's just say that I, now instead of being pure, I have it in a 1 molar sodium bromide solution. Now, if you go to look at the tables, you won't find a KSP for sodium bromide. You only have KSPs for insoluble salts. So all salt from Gen Chem 1 solubility rules, all salts of alkali metals are soluble. So this is a large value, and it's a Gen Chem 1 problem. If I have 1 mole of sodium bromide, I have 1 mole of sodium dissolved and 1 mole of bromide dissolved. So I have a common ion effect. That is NaBr. What I should have done on this top one is given a two-way arrow, but I was showing the dissociation. In reality, there's an equilibrium. For the sodium bromide, there's really a one-way arrow. Na plus Br minus, okay? Now, so since it's one-way arrow, I have a common ion. This adds bromide, which now adds this. And then from Le Chatelier's principle, imagine I had the top equation. If I added bromide, it's going to consume what I add, exam 2, and it's going to push the equilibria this way, meaning we would hypothesize that the bromide ion concentration would go down. And the bromide ion, as it pushes it that way, it's also consuming lead. So the lead concentration goes down. But as the bromide goes down, so does the lead. Therefore, I can remove the lead from the water through the common ion effect. Okay? So let's do this one. And what we're going to do is we're going to do this out the long way with an ice diagram. Okay? So here I have my PbBr2, and I'm going to put the solid here. And this is at equilibria with my Pb plus 2 plus my 2Br minus. Okay? Now, this is a solid. And remember now, I have to have the solid. This is an equilibrium. Okay? A saturated solution is when I have dissolved ions in equilibrium with the solid. Okay? Now, I started with none of this because I didn't have any common ions with lead, but I have a 1 molar solution of this. Okay? Now, normally we don't put the M there. Okay? But it's implicit that these are concentrations. Is everybody following me? And now, for every one of these that I dissolve, as long as I don't dissolve it all and could dissolve more, I make one of these and I make 2 of these. So now I have my equilibrium expression, and I'm just going to put a solid here. It doesn't matter how much I have, okay? So it's not a concentration. But obviously, if I ran out of lead bromide, and if I could have added more, then I don't have a saturated solution, and we're talking about a saturated solution here. So I have X of this, and I have 1 plus 2X of this. Now, in the absence of the 1 molar, and the top part, in part A up here, let me just call this A, I'll call this part B. In part A, when the bromide was 0, the value of the X was 0.0118. Now, because of Le Chatelier's principle, it's going to be less than 0.0118. But also, if I look at this, 1 plus 2 times X is equal to 1 plus 0.0236. And if this number is known to one significant digit, then the value of 1.0236 is 1. So I can ignore the X in my equilibrium expression. In other words, my K is equal to X times 1 plus 2X squared, and I have a cubic problem, okay? But I can ignore the X because it's so small compared to what I have, my initial concentration. So now I have K is equal to X times 1 squared, which is X, which is 6.6 times 10 to the minus 6. This is the value of K here. Okay? And so what we see is that in the presence of the common ion from the sodium, right here, there's a minus sign there, the concentration went from 0.01 molar to 0.00006 molar, okay? So Le Chatelier's principle shows that the common ion suppressed the ionization.